Alright guys, welcome back. In today's video, we're going to jump straight into our first section of Chapter 1 here in Algebra 2. Our first section is called Sets of Numbers. Now, where you've been in your previous algebra class, before getting to Algebra 2, you've been working with properties of real numbers, simplifying numeric expressions using order of operations, exponents, and using variables, expressions, and equations to represent real-world situations. In this chapter, the first of Algebra 2, we're going to be using sets of numbers and their properties. We'll be simplifying algebraic expressions and expressions with exponents, and we'll be using functions and their graphs to represent real-world situations. And then we'll be headed into being able to, for example, quickly calculate tips and discounts in our head. We'll be building a foundation for our calculus classes, and we'll be observing patterns and relationships in science and social studies throughout the course. All right, so let's take a look at our vocabulary terms. We just have simple here, so we don't get too overwhelmed. But throughout this chapter, we'll be looking at these terms. A set is a collection of items called elements. An element itself is an individual item that belongs to a set. A subset is a set whose elements all belong to another within a larger set. An empty set is a set that contains no elements at all. It's not the same as 0. Roster notation, listing the elements of a set between braces, like such. Finite set, a set with a definite countable number of elements as opposed to an infinite set, which is a set with an unlimited number of elements. Interval notation, this is notation using brackets, inclusive, and parentheses, exclusive, to describe a continuous range of numbers. Set builder notation is notation that defines a set by stating a property its elements must satisfy. For example, x is greater than 3 within our brackets. And then the domain, the set of all possible input values for a function. We'll use that later. All right, now within this section particularly, we see we have set, element, subset, empty set. Let me zoom in. Here we can think about the vocabulary words from a different angle using the word origins and everyday meanings. So for example, a subset. The prefix sub means under or below. Think of a submarine under the sea, or a subtitle, the text below the screen. A subset is a set that fits under or within a larger set. Element is next. In everyday language, an element is a basic substance like hydrogen or oxygen, but in math, an element is a basic member of a set. Just as oxygen is one element of the periodic table, the number 3 is one element of the set 1, 2, 3, 4, 5. Function. A function is something that performs a job. A thermometer's function is to measure temperature. In math, a function is a rule that assigns each input exactly one output. It performs the job of pairing. So think about hitting that button on the vending machine. You hit E4 and the Snickers comes out. That's a function that does that. Transformation. To transform means to change the form or appearance of something. A mathematical transformation changes the position, size, or shape of a graph while keeping its essential structure intact. And we'll be looking closely at those when we are graphing. All right, so there's a real quick rundown of our key vocabulary terms here in section 1 of chapter 1. Now let's take a look at our visual here. Zoom in real fast in our table. By the way, by the end of the lesson, we're going to be able to identify what kind of number any real number is. And order real numbers by converting to decimals and comparing, and describe any set of numbers using words, roster notation, interval notation, or set builder notation. That's where we begin here in Algebra 2. All right, so we're going to classify numbers by their type and represent the sets of numbers in different ways, in other words. Let's take a look at our visual here. So every real number fits somewhere in this hierarchy. The sets are nested, as we can see here with our oval shapes. So every natural number, for example, every natural number is a whole number. Every whole number is an integer. Every integer is a rational number. And every rational number is a real number. So they are nested. Now, rational numbers are real, but they're just not rational. So we'll talk about that here in a second. For example, -5 square roots of 3, or pi, or the square root of 2. Not the square root of 4, for example, because the square root of 4 is 2, which is a rational number. So be careful with our perfect squares when it comes to our radicals and our considering the exponent squared or to the second power there. Now, I say that because there's an understood 2 here. We don't write down. But if there was a third root, it would be different, a fourth root. This would be exponential decrease, right? Understood 2, so we say the square root of 2. Square root of 7 divided by 2, e. We have our irrational numbers. All right, so is every integer a natural number? The answer is no. Negative numbers and 0 are integers, but not natural numbers. Now, students oftentimes confuse whole numbers and natural numbers. So let's note that natural numbers do not include 0. However, whole numbers do. So natural numbers begin at 1, in other words. Now, some texts will define natural numbers to include 0, but that's not what our text. We use Golden Standard textbooks, Golden Standard American textbooks here for our all our courses. So we are going to include 0 in our whole numbers, but not in our natural numbers. And we'll follow that throughout the course. That's the convention of our textbook. All right. So let's go take a look at our next section. Rational numbers can be expressed as a quotient or ratio of two integers where the denominator is not 0. The decimal form of a rational number either terminates, such as 1/2 equals 0.5, or it will repeat, as in -4/3 equals -1.33333 forever with our repeater bar over that. Irrational numbers such as the square root of 2 and pi cannot be expressed as a quotient of two integers, and their decimal forms do not terminate or repeat. However, you can approximate these numbers using terminating decimals. So, is 0.333 rational or irrational, and why? It is rational because it is a repeating decimal that is approximately equivalent to 1/3. What about the square root of 4? Would the square root of 4 be rational or irrational, and why? Rational because the square root of 4 is 2, which is an integer. Now, we talked a little bit earlier that some students may assume that all square roots are irrational, but perfect squares have rational square roots. All right, with that being said, let's go ahead and jump into our first example. We're ordering and classifying real numbers. Zoom in on that. We're considering the numbers 0.6 with the repeating bar, 0.66666 on and on forever, square root of 2, 0, -5 halves, and 0.5129. So because we cannot compare numbers accurately unless they're in the same form, we want to convert everything here to a decimal, then we can order them mentally on a number line. So let's go ahead and do that. We have 0. Make my pen a little bigger. We have 0.6, which is going to give us that 0.6666 on and on. Then we have the square root of 2. Pop that into our calculator. We get 1.414. Okay. 0 is just 0.000. And then -5 halves will get us to 2.500, and then 0.5129 is already in decimal form. So which of these numbers, for example, is the most negative and therefore the smallest? This is negative, by the way. I meant to write negative there. -2.500. This will be -5 5 halves there. All right, so that will be the smallest. So we can write these in order. Let's go ahead and start to write these in order. We have negative 2.5, okay, is less than, what's next? 0, because we have no more negative numbers, right? Okay, is less than, we'll continue this on, is 0.5 or 0.6, for example, bigger. 0.5 will be slightly, or smaller, I should say, sorry, smaller. 0.5 is slightly smaller, so we'll write 0.5129 as slightly smaller than 0.6666. Okay. And then we have one more, 1.414. All right, so we can use our inequality symbols there, less than, to show that order, from negative 2.5 all the way up to 1.414. So least to greatest, if we go back to our original problems, we're going to have negative 5 halves, 0, 0.5129, 0.6 with the repeating bar, and the square root of 2. Now, just remember in class, you're going to be expected to write the original forms in the final answer. So even though we did convert those in order to compare them more easily, we're not going to write down the decimal approximations in our answer unless otherwise asked. If so, then go ahead. All right, let's go on to our next problem. Exercise B. All right, so consider the numbers 0.6 with the repeating decimal, square root of 2, 0, negative 5 halves, and 0.5129 from our previous example, and classify each number by the subsets of the real numbers to which it belongs. Use a table to classify the numbers. So let's go here, for example, the square root of 2. Now we're asking, for each of these, is it real? Always yes for our purposes, right? So we have every single checkbox on there, every single box checked. And then we ask ourselves, is it rational or irrational? And then if rational, is it also an integer, a whole number, or a natural number? So for example, the square root of 2, is it rational or irrational? Go all the way over here. It's irrational because it cannot be written as a fraction and its decimal is non-terminating or non-repeating. Okay, now we can fill in our table row by row. For example, negative 5 halves. Negative 5 halves is real and rational only. How about 0? Real, rational, integer, whole. In other words, R, Q, Z, W. 0.5129, real and rational. 0.6, with the repeating bar over it, real and rational as well. And then we already covered the square root of 2. So, why is 0 a whole number but not a natural number, for example? Let's go back and look at our visual here. This is standard mathematical convention, which is what our textbook uses. So for example, N will include 1, 2, 3, and on. But W is where we get to bring in 0. 0, 1, 2, 3, and so on. This is just standard mathematical convention. All right, let's check out 1A. All right, so here we will apply the same process by converting to decimals, then we'll order them. So for example, what's the decimal approximation for pi? Let's start there. All right, so pi is approximately 3.14159. And what about our negative square root of 3? Our negative square root of 3 is approximately, if we put that into the calculator, let's use our approximate symbol there, approximately negative 1.732. So now let's order these. Here they are. Again, let's go ahead and order these. With our inequality symbols, we'll switch to a different color. Negative 2 is less than negative square root of, right, we do that one. Negative square root of 3, right, which was approximately what, negative 1.732, which is less than 0.321, or sorry, negative 0.321, which is less than 3 halves. By the way, that's about 1.5, right? Which is less than pi, which is approximately 3.14159. All right, so least to greatest, if we're writing these out, let's go back here and we can write down, okay, negative 2, negative square root of 3, that's better, negative 0.321, 3 halves, and pi. All right, let's take a look at 1b together. So our instructions are classify each number by the subsets of the real numbers to which it belongs. All right, well, let's start with negative 2. We'll go back to our chart here to help us. Negative 2 is real. It is a rational number. It is an integer. All right, let's go write that down. For negative 2, negative 2 is R, Q, and Z. What about pi? Let's go to pi next. Go back to our, oh, there's pi right there, right? It is real. And it is irrational. Irrational, so we can just write irrational there. So we have real and irrational. Let's go back here and we'll write R, and we'll just write that out, irrational. With our double R there, irrational. Okay, what's next? Negative 0.321. All right, let's go back to our chart here. This is quite handy for this type of problem. Negative 0.321, okay, that's going to be real. And it has a terminating decimal, so it is rational. Real and rational. Let's label it R and Q because it has a terminating decimal. Okay, what's next? 3 halves. Go back over here. For 3 halves, we have real, and it is rational. Let's label R and Q. And we have negative square root of 3. Negative square root 3. Okay, let's write that down. Negative square root of 3. Back over to our handy visual. For negative square root of 3, we have real and irrational, because it's not a perfect square, right? And for all intents and purposes, these are all real numbers. So we'll put a R. We're not at imaginary numbers, right? Not quite yet. We put a R, and this will be, we'll spell it again, irrational. All right, that's how we would do 1B. This will terminate our first part here, part 1 of 1.1, our first section of chapter 1. In our next video, we'll cover part 2. See you soon.